Assalamu alaikum, my name is Ayila Naeem and here is my lab report number 7 of digital signal processing. The objective of this lab is to study digital sequence in terms of frequency spectrum, contribution of high frequencies in a signal and contribution of low frequencies in a signal. In task 1, the sequence is given and the sampling frequency is up to 20 kHz. Plot the original signal. For the plotting, we use the time vector t, which is divided by the frequency sampling. Plot the figure. Give them title and x label, y label. Now perform the Fourier transform, which is x is equals to fast Fourier transform, and give an frequency analysis. Frequency analysis is equals to line space 0 frequency fs and length x. Now plot the frequency spectrum. In the next line, remove the frequencies up to above 5 kHz. X filter 5 kHz is equals to x, and x filter 5 kHz, which is frequency is greater than 5000, which is equals to 0. Now perform inverse Fourier transform. X filter 5 kHz is equals to inverse fast Fourier transform. Plot the filter signal 5 kHz cutoff. Now redraw the signal after removing frequencies above 7 kHz and remove the frequencies above 7 kHz. And in the next step, perform inverse Fourier transform and plot the filter signal 7 kHz cutoff. Now plot the frequency spectrum after 7 kHz cutoff, and the resulting output is this is the original signal, which shows the amplitude. The frequency spectrum shows the magnitude. Filter signal cutoff at 5 kHz, which shows the amplitude, and filter signal cutoff at 7 kHz, and at the last frequency spectrum after 7 kHz cutoff. In task number 2, read the audio file. Replace the music.wave.aac with the path of your audio file. Now calculate the DFT using FFT. DFT is equals to fast Fourier transform y. Now obtain the length of the DFT, which is n is equals to length DFT. Calculate the index where the upper and lower half values of the frequency begins. Index upper is equals to CL n divided by 4, and index lower is equals to floor 3 multiplied by n divided by 4. 0 of the upper half of the DFT coefficients. DFT index upper end is equals to 0, and reconstruct the audio sequence using the inverse DFT for upper frequencies. Play the modified audio with upper frequencies removed. In the next step, 0 out of the order half of the DFT coefficients. Reconstruct the audio sequence using the inverse fast Fourier transform for lower frequencies, and play the modified audio with lower frequencies removed. And the resulting output is by removing the upper half of the frequencies. It causes removing these high frequencies, the sound may lose its brilliance and clarity, and the piano sound becomes softer and less sharp with a smoother and less edgy tone. By removing lower half of the frequencies below 3 fs divided by 4, it removes these low frequencies. The sound loses depth and richness, and the piano sound may become thinner and less resonant with a less impactful presence. Thank you so much for watching my video.